3.7 is the section on the topic of implicit differentiation. To sort of get the idea for why we might need implicit differentiation before we learn how to use it, just consider this beautiful picture. This is a circle, and you might remember from whatever work you did in Algebra 2 or just in your discussion of functions that an equation for a circle does not represent a function. I can look at this picture of a circle. If what you think of for function is vertical line test, clearly this fails the vertical line test. I could try to isolate the y to make y a function of x, but in that process I'm going to have to write something like plus or minus when I take the square root. And that's not an explicit formula for y in terms of x. But there's lots of cool things about circles. There's no reason we wouldn't want to maybe find the equation of the line tangent to the circle. So we can look at this picture and understand what the slope would mean. So we want a technique, a mathematical technique for finding an expression for the slope of this circle at any point, even though I won't be able to isolate the y and write this as y, write y as a function of x. So one more reminder before we talk about how implicit differentiation will work. A quick reminder about the chain rule. So this, we said, it's one version, it's one way to think about the chain rule. If I just made up these functions, y is 3 times u, and u is x to the 5th. If I want to take the derivative of y with respect to x, I have a big problem because when I look at the function y, x is not the variable of that function. So in this particular case, I could rewrite this function and make a substitution of x to the 5th everywhere I see u, but I'm not always going to be able to do that. So we're just using this as an example to remember what the chain rule tells us. And here, we might not have used these words before, but this is a big idea. Consider writing this down. What's going on here is I want to take the derivative of y with respect to x. This is the thing I want. This is the thing I'm used to finding. But I have this big problem when I sit down to do it, and that's that y is not a function of x. In this case, y is a function of u. I can accomplish the process, this problem of taking the derivative of y with respect to x, if I remember the chain rule. So instead of finding the derivative of y with respect to x, I can find it in this roundabout way by taking the derivative of y with respect to the variable that's actually in y. In this case, that's u. So it's the derivative of y with respect to u. The derivative of 3u with respect to u is 3. And multiplying by the derivative of u with respect to x. Well, I can look here to find u. U is a function of x, so when it's time to find the derivative of u with respect to x, there's no problem. That's going to be 5x to the 4th. So the derivative of y with respect to x is the derivative of y with respect to the variable that's there times the derivative of that function, that u function, with respect to x. So here I get 15x to the 4th. So I remember that pattern because that's what we're going to need for implicit differentiation. If you want to take the derivative of some function with respect to a variable that is not there, then take the derivative with respect to the variable that is there and multiply by whatever the derivative of the variable you used with respect to x is. All right, now let's look at that first example. All right, so here's that circle problem. This is that first example on your handout, and I'm expecting you're writing these examples, these notes in as you go. If you have questions about what I say, or you want me to re-explain it again tomorrow, that's totally fine, but I'm expecting that you're writing these steps in as we go. So x squared plus y squared equals 1. It's the equation of a circle. We said a few minutes ago, it seems like it should make sense to talk about the slope of that circle at a particular point. But we're not going to be able to isolate y in order to use our regular derivative techniques. So we're going to be taking the derivative implicitly. If I had y as a function of x, then I'm taking the derivative explicitly. So here implicit just means the opposite of explicit. So the good news is that all those things you remember about solving equations, you could do something to both sides of the equation as long as you do it to both sides, like divide both sides by 7, or square both sides, or take the square root of both sides. That works with derivatives too, and antiderivatives, which we'll talk about second semester. So my technique for finding dy dx, that's what I'm going to call the slope, right? The derivative of y with respect to x, is to take the derivative of both sides. The problem is saying take the derivative of both sides of the equation. That's not quite specific enough. I need to specify that I'm going to take the derivative of both sides of this equation with respect to x. Because the thing I'm looking for, let's get this here just to remember, the thing I'm looking for, the derivative, is the derivative of y with respect to x, dy dx. So in order to get that expression in my new equation, I'm going to need to take the derivative of both sides with respect to x. So just remember that operator we said we could use. That's this, d dx means take the derivative with respect to x of x squared plus take the derivative with respect to x of y squared is going to equal take the derivative with respect to x of 1. You might get to the point where you don't actually write that d dx in here, but you need to know what's happening, which is I'm taking the derivative of every single term on both sides of that equation with respect to x. Okay, we'll do the easy parts first. What's the derivative with respect to x of x squared? It's easy. It's 2x. Do the other side. What's the derivative with respect to x of 1? Well, the derivative of any constant with respect to any variable is 0. The tricky part is going to be figuring out what the derivative with respect to x of y squared is. And that's why we had that reminder a couple of minutes ago about what the chain rule can help us with. I want to take the derivative with respect to x of y squared. Well, y squared doesn't have an x in it. So the way to take the derivative of y squared with respect to x, is to take the derivative of y squared with respect to y, which is pretty easy, 2y, and then multiply by that missing piece, which is dy dx. And that's good, because that's the thing we want to find, dy dx, and now we're going to have that in our expression. Let me figure out how to advance this slide. Okay, so just to make sure nobody missed anything, I'm taking the derivative of each term with respect to x. The derivative of x squared is 2x, that's where this comes from. The derivative of 1 with respect to x is 0, that's where this came from. The only part that's tricky and a little bit new is when it's time to take the derivative with respect to x of y squared. That's going to be the derivative with respect to y of y squared, which is 2y, times the derivative of y with respect to x, which we just call dy dx. That's where this expression dy dx comes from. It's going to be important as we move on that you remember that dy dx, it's not a fraction, it's not a division problem. It's one single entity, dy dx, which means a function which is the derivative of y with respect to x. A function which tells us the slope of y, the slope of the function with respect to x anywhere. Okay, so now that we have this equation, 2x plus 2y dy dx equals 0, what was I trying to find at the beginning? I was trying to find dy dx. Notice I have an equation with dy dx in it. My goal is simply to isolate the dy dx. So move me out of the way. So I'm going to leave everything that has a dy dx factor in it on one side and move everything else to the other side of the equation. So that's subtracting 2x from both sides. Now I'm trying to isolate dy dx, but dy dx is being multiplied by 2y. So divide both sides by 2y, and you can cancel out that 2, and we get negative x divided by y. Notice if you were on the free response section and you left your answer like this, that gets full credit. That's no problem. But notice we can simplify too. That's kind of interesting. This might be our first time if you haven't looked ahead into your free response notebook. The slope, dy dx, right? The slope of this circle non-function isn't just related to x. It's not a function of just x. It's related to both the x and the y. So we're going to see that happen a lot more as we proceed with our study of derivatives. But we have a function now whose derivative is a function not only of x, but also of y. So if you're willing to indulge me for just a moment, I want to help you avoid a really common error that happens when students learn about implicit differentiation. I appreciate that I've been harassing you kind of a lot about labeling your work, and I appreciate that you've been doing this. So students who are focused on making sure they label all their stuff sometimes put a label in a place where it doesn't belong. So would you put your pencil down, because I do not want you to be tempted to write what I'm about to write. Put your pencil down. What I'm about to write is not correct. And I want to show you why, but I want you to see what it looks like so you know and you can make that connection why this is not correct. So Mrs. Hicks says I should find the derivative dy dx, and I know I'm supposed to label it. Well, in every other problem where you found the derivative, it would be correct. You started with y is a function of x, and you're going to take the derivative. When you take the derivative, you get dy dx, the derivative of y with respect to x. So some people are in the habit of just saying, okay, well, I'm going to take a derivative, and I'm going to label it dy dx. And I don't know, you say that's equal to, and now you start taking a derivative. Well, the derivative of x squared with respect to x is 2x, plus we just learned implicit differentiation. The derivative of y squared with respect to x is 2y dy dx, and the derivative with respect to x of 1 is 0. But look what you did. This part here, we didn't start with a y and then take the derivative of y with respect to x. This part here is completely not correct. It is not appropriate to label your work here dy dx. Your work was taking the derivative of each term with respect to x. That's a technique you know from past algebra experiences. We can operate on an equation as long as we operate in the same way on both sides. So you were taking the derivative of. You were not identifying a derivative. You found dy dx, kind of. It's still trapped in here and we have to isolate it. So you have to not accidentally start a habit of labeling your work here dy dx. What you're doing is you're taking the derivative with respect to x of each term in that equation. So I hope you had your pencil down that whole time so you didn't accidentally write dy dx. But I just want you to notice if you labeled that, you just told a big math lie. You said that dy dx is equal to 0, which is definitely untrue in this situation. So to put one more point on that, remember, if you write dy dx equals, then you're telling me that dy dx equals 0, which is definitely not true because we just figured out a second ago that dy dx is equal to negative, what was it, negative x over y, negative y over x. Okay, so that's an important point about labeling for implicit differentiation. You are not labeling because you have not found something yet. You are going through a process of differentiating with respect to x. Your job later is to isolate that dy dx. That's when you're going to have your label.